Okay, that was fast 2 minutes. The next talk is going to be on DC to DC converters.
Okay. Does it work with this? Because I'm not sure.
By Zoe Böhle.
I have this.
She's an enthusiast for open hardware and fan of DIY, and has been working on the topic of DC to DC converters for a long time.
And I'll get to work.
And I have to keep on talking now because it seems that her computer is not really communicating with the presentation device. We do have a picture, but we don't get it moving.
Come back and press the key. Okay, I'm gonna. Because this can work. This is working. Okay, this one's working. From this distance. Okay. Yeah, that's.
While we're still having some issues up here, I might remind you that it is very helpful if you take your trash with you. And now please welcome Zoe, and we are ready to roll. Give her a warm hand.
Hi. My name is Zoe, and this is the first time I'm standing here on a chaos stage, so I'm a little bit anxious, but I'm here to talk to you. I'm here to talk about DC-DC converters, and the talk's called DC-DC converters and everything you wanted to know about them, but it's unlikely I can fit everything into a 50-minute talk, so it's not everything. But my goal is to provide you some starting points and give you an overview. And hopefully, if you already worked with DC-DCs, then you're also not gonna be annoyed and not gonna be bored. So before I start with the DC-DC topic, I would like to ask you to be excellent to each other, and this is not related to my talk, but I hear people starting clapping when someone breaks a bottle accidentally, and I think that's super not cool. So yesterday I saw someone breaking down in tears because they just broke a bottle and everybody was clapping and paying attention to them, and that was like harassment. So please don't be the one who starts clapping. But also, I'm not here to forbid you to clap, and just know what's happening. So, brief introduction to DC-DCs and why. Quite often, you need different voltages than what you have available. For example, you have a microcontroller, or you have an FPGA, and you work with a battery, then you need to provide a different voltage for that circuit. And the trivial solution is to just use two resistors and make a voltage divider, but this is totally unsuited for power delivery, because as you start loading the output voltage starts dropping. Also, this circuit dissipates power even if there is no useful load on the output. So this is only useful for signals, and to have some kind of feedback and regulate the output to a desired level, you can use an LDO, which is the same thing, but you control one resistor, very simplified, to always keep a desired output voltage. Of course, this can only go lower than your input, and your efficiency is limited to the ratio of the output voltage and the input voltage. And this is even an ideal situation. So instead of burning up power in your converter, you can just use switches. And this is the idea behind switching supplies, that you use a switch element which is either fully on or fully off. And if it's fully on, then there is no loss on the switch. And if it's fully off, there is no current flowing through it, so there is no loss either. There are some practical problems with this approach, but this works for LEDs and heaters if your switching frequency is high enough. To think of a DC-DC converter is a box with 4 terminals. It has an input side and an output side. And right now I'm talking about buck step-down DC-DC converters, which are non-isolated. This means the ground in the input side and the ground on the output side are connected together inside. And this limits certain uses. Also, you should not connect these DC-DC converters in series. So if you have a block like this and you think, oh, I could use 2 or 3 of them and just connect them in series to deal with higher input voltages, that's going to blow up very quickly. A block looks like this on a screen and might look like this in reality. And let's take a look inside. So all of these DC-DC converters consist of a power stage, a control system, and a feedback. And the feedback is there to provide a regulated output regardless of the operating conditions. So what's inside a power stage? To have a deeper look inside, we can consider this asynchronous buck converter, where a switching element, a MOSFET, is controlled by an analog and digital circuitry. Feedback is provided from the output voltage, and we see a diode in the middle, which I'm going to talk about soon. You also see 2 capacitors on the input side and on the output side, which are also very important. More about them later. Let's consider the first situation. The switch is on. This is so-called the on state. And this forms a loop from the input to the output. So the input capacitor we can neglect, and in an ideal situation, the output capacitor is I will talk more about the output later. Sorry. Oh. All right, I don't want to make this into a lecture and everybody's sleeping in, and the fun part will start very soon. So this DC-DC has 2 states. Either the switch is on or the switch is off. Right now the switch is on, and you see that the current can flow from the input through this inductor to the output. The inductor resists the change of current. It's like pushing a heavy mass, and once it starts moving, it wants to keep moving. That's why in this on state, the input current flows through the inductor and starts to increase, while it's also flowing to the output. Then the converter turns the switch off, which comes to the off state, and now the diode comes into play, which will keep the current recirculating. in this off state, there is no current from the source to the output, but the output is still powered from this decaying magnetic field through the inductor. And sometimes you hear about synchronous DC-DC converters where this diode is replaced by another switch. In that case, efficiency is increased since the voltage drop across MOSFET is lower than the forward voltage of the diode. So in this case, as you can see, current is still being delivered to the output. And this is the big advantage of the buck converter, that in both in on and both in off states, the output is sourced with current. And so what the output capacitor does there is it provides the difference between the inductor current on the lower end. You can see the inductor current as the switch is on, it ramps up. As the switch is off, it ramps down. And in the middle, you see this line, which is the output current. So you see these triangles, and this is what's provided by the output capacitor. All right, so this is an actual part without the simplifications. And I would like to talk a bit about the reference voltage and how that works. So this device creates an internal 0.7 volt reference. And you can program the output voltage by choosing R1 and R2 on the left side. So at your desired output, exactly 0.7 volt will be at this voltage divider. And this converter will keep regulating to reach this state. There is, if you're looking for a DC-DC converter to your next project, then you might see a bunch of parameters, and I'm going to talk about those. So first, you see a 3.3 volt 2 amp converter. What does it mean? This depends on how and who specifies that output, because someone says it's 2 amps if it can provide 2 amps for a second, and someone says it's 2 amps if it can continuously provide the 2 amps even in a warm environment. So it's important to talk about if it's a peak or continuous current rating. Then there is this so-called output ripple. You saw that switching action going on and off, and that will create a ripple on the output voltage. So it won't be 3.3 volt, it will be oscillating around that. This can be as low as a few microvolts and as high as a few volts, depending on the parameters. Also, there is voltage accuracy. So maybe it's labeled as 3.3 volts, but actually it's 3.5 or 3.0. Load regulation. It's maybe 3.3 volts when it's unloaded, and as you increase the output, it starts changing the output voltage. There is the line regulation, which means the input voltage has influence over the output, which is undesired. Then there is this maximum input voltage rating. Let's say this converter can tolerate 7 volts on its input. So you think, oh, let's just hook it up to USB. That's 5 volts, right? Yes, but no, because when you use cables and non-ideal conditions, you can create transients which overshoot the voltage possibly way above this maximum rating. And this can lead to very nasty surprises, because sometimes they fail short, which means they connect their input directly to their output. In this case, the device you connected to the converter might also go up in flames. So mind the transients, and always have some margin between your desired input voltage and the maximum the converter can tolerate. Then you might see 95% efficiency, and that's also a question at which load, because at maximum specified load it will be lower, and at less load it will be also lower. So there is this efficiency peak what marketing people love to specify. There's also this so-called quiescent current, which means your converter draws current from your input even when there is nothing on its output. And if it runs from a battery, this can drain your battery in days or weeks. So you must pay attention to this. And there is this other factor called switching frequency. So how fast, how often the internal switch changes state. But this might not be a constant value, especially with the previously mentioned quiescent current feature. The converters that excel at having a low quiescent current don't have fixed switching frequency. So you might have noise at different frequency bands and disturb your circuits or radio noise. Let's talk about a few features you might want to look for. Enable functionality. This is very useful to easily disable your DC-DC converter and without having to interrupt either the input side or the output side. Let's say you have a 20 amp output converter. You really don't want to switch the 20 amp with a mechanical big switch. And instead of that, you have a logic input to your DC-DC converter with which you can turn this completely off. Then there is a so-called undervoltage lockout. You might want to prevent it from running below a certain input voltage to prevent draining your battery too deep and turning it completely off. There is this power good that can provide information to your processor that the output voltage is in regulation and stabilized. So if you hook up the power good output to, let's say, a reset line or enable, then you can be sure that the output voltage is already stable and it's not going to go, your processor not going to go into glitch. Over temperature shutdown is very common these days, and that makes these tiny converters almost indestructible, because if they get too hot, they just turn off completely before they get permanently damaged. Efficient standby, this is the so-called low quiescent current option. That means if your output is off, your processor is sleeping, then it will reduce switching action to reduce switching losses and might only draw a few microamps or even nanoamps. Very important for battery-powered applications. Then you might see overcurrent protection, which makes the output very robust. You can even make a short circuit, and the overcurrent protection will limit the output current to this value. And this prevents damaging of the converter and also damages to the cables and switches if they are rated to withstand the overcurrent protection limit. And let's talk about noise. The output ripple is not exactly noise. Output ripple is there because the output capacitor is non-ideal. And usually this is very low in a properly designed converter. But if you measure the output, you might see spikes on the output. And that's not a ripple, that's conducted EMI. Because on that inductor, the windings are coupled very closely. There is some capacitive coupling between the wires. So the digital on-off action from the switches will propagate to some extent to the output. And this is attenuated by the capacitors, but they cannot be completely filtered off. And you will see the switching frequency and even upper harmonics of it. But this can also be filtered. And there is also radiated EMI, which comes mostly from the switching node and capacitive coupling to the ground plane. And also the inductor, if it's not shielded, then a magnetic field can also radiate out and cause interference. On this picture, what you see is that gray block. That's a shielded inductor. And the two blue connectors at the end of this PCB are screw terminals. And I personally advise against using this style of screw terminals because the wires can easily slip out, make a short, or you don't notice that they're not connected. So I prefer a different style of connectors. Okay, so it's good to know about non-ideal components. The capacitors that are used have a so-called DC bias. These ceramic capacitors, multi-layer ceramic capacitors, are very sensitive to the DC voltage across the terminals. And if they are rated, let's say, 20 microfarads, at their rated voltage, they might lose up to 90% of their capacity. So you always have to pick a capacitor that's rated to a higher voltage than what your output is to compensate for this effect. And you also need to put more capacitors at your output as what you would think in an ideal situation. Mind the transients. As I said, if you plan to hot plug, connect to live wires, your converter, you have to keep in mind the inrush current. Those capacitors, when they are fully discharged, and you connect that to the input, then they will try to charge to the input voltage as fast as the cabling lets that happen. And the cables have inductance, which will store energy and overshoot the input voltage. When fiddling with MOSFETs, don't forget the ESD protection. And MOSFETs are very sensitive at their gate because the oxide layer is so thin that even 20 volt voltage is enough to break it down. And a 20 volt ESD strike is something you probably don't even notice, but it can damage the MOSFETs. And avoid the 7800 series LDO because that's a very old part, and I still see it in new designs, while there are much better ones with better regulation, less quiescent current, and that's also an LDO. So it's like just marginally related to DC-DCs. If you make your own DC-DC converters instead of buying one, you should read the datasheet and follow the instructions, because the manufacturers give you a proven, tested layout, which is typically good advice to follow, and you should only deviate from that if you know what you're doing. I'm sorry. Oops. All right. That mostly concludes what I was what I was trying to talk about, and now it's time for your questions.
Now, there are two microphones, one there and one over there. Usually there are... here comes the light. Are there any questions? How about the Signal Angel? Does the internet have any questions? The internet doesn't have a question, but here's one up front. Go ahead.
Hi, what would you recommend instead of screw terminals?
That's a very good question, and that really depends on the application. You can have different kind of screw terminals which use either cable, like crimped terminals on the cable. So you have a cable shoe.
Like a ring or something?
Yes, like a ring,
Okay.
because then there is no way that it can slip out. For less current, you can use DuPont connectors. They can take like 2-3 amps per contact. The standard pin header and that kind of thing. And there are also latching connectors from Molex and other manufacturers also. The problem is with that you need crimping tools, and those can be very expensive. So it first makes sense to get those when you have a hackerspace, or you can share it with other people.
The next question, please.
Thank you for your talk. On your last slide, last point, you mentioned stability analysis. What is your experience with running such converters in parallel for redundancy, and how would you do the analysis there?
Running current mode converters parallel is typically okay, but they won't do current sharing automatically. So as one converter has a certain output voltage set, and the other one has different, little bit different voltage, and that will create a difference in their output currents. And there are topologies and there are converters which are prepared for parallel operation, and they can provide current information to all of the parallel converters, and they can automatically synchronize. For stability, that should not influence the stability of it. What I should have mentioned is stability analysis, because we have a control loop. the control loop takes the output and creates a control signal that influences the output. But this loop has a delay. And because of this delay, if there are... Yeah, basically you can make an oscillator of this. And to avoid that, you can use a network analyzer and inject a signal into the converter, and then the drill.
Thank you.
Yeah, you go ahead over there.
Hi. What would you say the choice is between a dissynchronous mode or a forced synchronous mode of?
That's a very good question. All right, so when I talked about this briefly and mentioned the synchronous converters, with forced synchronous converters, you have a controlled switch, and those have typically fixed switch frequency. If the output current is 0, then during half of the period, current will flow backward from the output capacitor to the input side. And then the next half period, that current will flow back from the input to the output. So basically, energy swings between input and output. And this causes efficiency loss. But this also avoids operation in discontinuous mode, which reduces ripple and reduces EMI. Yes. So it depends on your application.
Thanks.
Okay. You're welcome.
The next question.
Hi, Zoe. Thank you for the talk. I have a question about, you mentioned linear regulators at the end. What are they used for in this context?
You mean the 7800 series?
Yes. Not the one before, I think.
Yeah.
Yeah, here.
So those were very good regulators in the 70s. And those are linear regulators. And the problem in the 7800 series, everybody knows about them because books are full with them, but they have quite a few milliamps of quiescent current. They also have bad regulation against load and line transients, and they're not cheaper than much better alternatives. So there's really no reason to use those. You can use, for example, a DC-DC pre-regulator and then an LDO afterward to smooth out the voltage.
Okay, thank you.
Go ahead.
Yeah, thank you very much. My question is, you mentioned the noise coupled via the inductor to the output. Which sort of filter do you recommend? Differential noise or common mode noise, and input or output? Which is most important from your perspective?
So lots of the noise goes actually back to the input supply. And I said that in an ideal circuit, the input capacitor is not necessary. But in a real circuit, the input capacitor is critical because the input inductance is seen by the switch. So if you, let me show you the, on this chart you see the inductor current, and the input current it follows the inductor current only during the on phase. which means after the end of the on phase and beginning of the off phase, it falls from maximum value to 0. And later on, at the end of the off phase and the beginning of the on phase, the current jumps from 0 to the output current. And these jumps in the supply current create an awful lot of EMI if the input capacitor is not large enough. So this is a very critical thing, and I saw quite a few converters where the input capacitor is underdimensioned, and when you run it over longer wires with more parasitic inductance, that can create a lot of EMI. For ways of reducing the noise on the output, the best way is to have proper filtering capacitors. If you use ceramic capacitors and a high enough value, you can get rid of the almost all of the noise. I made a design which had microvolt noise because I found a capacitor with its resonance frequency exactly at a switching frequency. So basically, all that noise that was coming from switching action was reflected away at higher frequency ranges where it got filtered, dissipated much faster. You can use pi filters at the output, but be mind that you worsen the transient behavior of your converter. So if your load suddenly needs a lot more power and starts drawing more current, then your converter will react slower because of the filter you just added. Yeah, pi filters or RC filters if you don't need that much current.
Okay, thanks.
Okay, great. I don't see any more questions, so everything seems to be fully explained. Thank you, and give her applause, and good night.
Thank you.